We now want to look at a couple single loop circuit examples. We're asked to find the voltage VR2, the voltage across this 620 ohm resistor. So the process is, one, we'll label the current, which I'm going to choose to go in the clockwise direction, though you could choose it to go the other direction. Two, we want to label all of the unlabeled voltages. This can be skipped once you get the hang of the technique, but we're going to do it explicitly here. So I see that R1 is not labeled, so I'm going to write VR1 across this. And I have chosen passive sign convention. I put the minus on the bottom so that the positive current I enters it. That's simpler and is more logical to do that. If you had written it the other way, then you'd have to say that VR1 was equal to minus R1 times I, rather than plus R1 times I. Okay, now number 3, write the KCL equation around the loop. KVL, and we're going to start in the lower left corner, and we're going to go clockwise. So we'll start and we'll go up through R1, and I encounter a positive sign, so I'll write plus R1. And then we encounter the negative sign of the 2-volt source, so I put minus V2. I encounter the positive sign of VR2, so I write plus VR2. And then I add, I encounter the plus sign of this voltage source, but the voltage source is actually a minus 5-volt source, so I'm going to write minus 5 volts. Now I've written my KVL equation. I'm supposed to be able to solve for the current from this, but I don't see the current anywhere in here. So what I need to do now is use the constituent relationship, the terminal relationship for the resistors, and re-express their voltages in terms of current, which I can do using Ohm's law. So VR1 is equal to R1 times I1, and VR2 is equal to R2 times I2, or times I. Now I rewrite my equation in terms of I, and I now have that one equation, one unknown, and we can solve for R, or for I. Combine the voltages here to get 7, bring it minus 7, bring it over to the right, and now we can solve I as being 7 volts divided by R1 is 380 ohms, and R2 is 620 ohms, for a total of 1K, and that ends up being 7 milliamps. Now we were asked to find the voltage across VR2, and I solved for VR1. Okay, well, VR2 is equal to R2 times I, which is going to be 620 ohms times 7 milliamps, and that is going to be something like 4.34, I think. Okay, let's move on to the next problem. Here we introduce a dependent source, which we haven't seen before. Okay, so we'll show how we do that. So again, we're going to use the same method, same steps. We're going to label I, which we have done. We're going to label all of the voltages in the loop, and I said you only need to do that when you're first starting out. I'm going to skip that for now. Well, I'll go ahead and write it here. We'll call this V8, and we'll call this right here V7. Okay, so then when we write KVL, starting at the bottom left and going around clockwise, I'm going to have minus Vx, then minus 12 volts, plus V8, plus V7, and then plus this voltage whose value is equal to 4 times Vx. Okay, now again, I could have labeled V8 and V7 with opposite polarities, and they would have minus signs in this KVL equation, but that would be okay. And you can try this, because later when I replace V8 with an expression involving current, and I would have used minus I times 8 ohms instead of plus I times 8 ohms like I will here. So it all works out in the end, but I think it's best to use the passive sign convention. So here we go, V8 according to my notation on the schematic, is equal to 8 ohms times I. And V7 is 7 ohms times I. Then we have 4 times Vx. Now what is Vx? Vx, if you look at it, that's the voltage across this 30 ohm resistor. And so it's going to be a R times I, but it will actually be, if you look at the polarity, it's not going to be 30 ohms times I. That's what this voltage would be. Okay, V30 would be 30 ohms times I, but Vs, or Vx, has the opposite polarity, and so it's going to be a minus 30 ohms times I. So now I replace Vx with minus 30 ohms times I. I pull out the I. So here we go. We get a minus Vx gets replaced with a plus 30. Then I have plus 8 ohms, plus 7 ohms, and then minus 4 times 30. And all of that is times I. You do the math for that, and we find that I is 12 volts over minus 75 ohms, or minus 160 milliamps. We were asked to find the power absorbed by each element, and so we're going to label the powers as follows: P12 for the 12 volt source, P30 ohms for the 30 ohm resistor, P8 ohms for the 8 ohm resistor, P7 for the 7 ohm, P4VX for the source. Okay, so P12, now we're talking about power absorbed, okay? So we have I times 12. However, if we look at the sign convention, look at the current I is coming out of the positive terminal, and so that's actually active sign convention. So if you have a positive I here, that means that's power delivered to the source, delivered from the source. And so the power absorbed by the source must be minus times that. Okay, 1.92 watts. Okay, so the power absorbed, and that may seem strange, the power absorbed by this source is 1.92 watts. That means that there is actually power flowing into that source. And where could that be coming from? Well, we know it cannot come from the resistors. They never supply power. So evidently, this guy over here is somehow supplying power. So let's continue. The power delivered to, or absorbed, by the 30 ohm resistor is just I squared times 30 ohms. And that's 0.768 watts. And for the for the 8 ohm resistor, it will be 204 milliwatts. For the 7 ohm resistor, 179.2 milliwatts. And for the 4VX controlled voltage source, it's going to be I times the voltage that it puts out, which is 4 times Vx. And what is Vx? So let's go ahead and plug this in. We'll start filling this out, and we'll substitute Vx when we get there. So minus 160 milliamps times 4 times, now Vx is minus 30 ohms times I, and I is minus 0.16 amps. So we get a double minus, a triple minus sign. And so you take the product of all of that, and it's minus 3.072 watts. And if you sum these 5 powers, they actually sum up to 0. And that is a good check. Okay, let's look at one more. This problem is actually simpler. However, there is a caveat with it. When you first look at it, you think, wait a minute, this is not a single loop problem. And it's not. There's 2 loops in there. However, let's look at what we're asked for. We're asked for finding the current I10, that's the current going through the 10 ohm resistor, and the current I60 going through the 60 ohm resistor. So the approach we're going to take is we're going to temporarily convert this into a single loop circuit. It's not the only way we can do it, but this is what we're learning, and this is what we're going to do now. We're dealing with single loops. So recognize that if we took these two resistors here, they're in parallel, and if we combine them in parallel, we could replace them with one resistor that would be 20 in parallel with 60, which turns out to be 15 ohms. And that's been redrawn right here. Now, if I have a 20 ohm and a 60 ohm in parallel on this original circuit, and I get some current I-10, whatever that is, and then I go to this second circuit here, where I have replaced the 20 ohm in parallel with 60 ohms with a single 15 ohm resistor, the question is, has I-10 changed from what it is here? And the answer is no, because we haven't changed the net resistance in that loop. We simply replaced two parallel resistors with a single resistor whose value is equal to the parallel value of the 20 and the 60 ohms. And now we have a single loop. In fact, it's very trivial. The current that's going to flow there is just simply the 10 volts divided by the total resistance in that loop. So it's going to be 10 volts. I-10 will be 10 volts divided by 10 ohms plus 15 ohms. Okay, that's what we see. I mean, I wrote KVL here, but that's not even really necessary. It's so simple. So once we have I-10, now the question is, how do we get I-60? Well, if I want to find I-60 and I know that that resistance is 60 ohms, then all I need to find out is what is the voltage across my 60 ohm resistor. If I know that voltage, then I can write I-60 is equal to V1 over 60. So V1 is what I need. How do we find V1? Well, I know what current is flowing into this node, and I've replaced that parallel resistors with a single 15 ohm resistor. So that means I can compute what the voltage is V1, and I've labeled it here on the right, V1 as just simply I times 15 ohms. And that's exactly what we're doing right here. 15 ohms times 2/5 of an amp, which is the current that's flowing, is equal to 6 volts. And finally, I can plug that 6 volts in here and solve for I-60. It turns out to be 1/10 of an amp. So in conclusion, we find that I-10 is 0.4 and I-60 is 0.1.